So during this session, during this hands-on session, we have a couple helpers who will go around and help people with the notebook and maybe some potential problems. Please raise your hand if you're a helper during the hands-on session so that people know who you can ask questions to. Okay. Okay, so also if you're a helper and you see someone that's walking around and has questions on their face, please. Oh. That's the timer. Feedback. That was feedback. Good. Okay, so helpers, please help if you see someone that has questions. Yeah, so everybody should have the Google Colab, the IPython notebook now copied to their own Google Drive folder. If you still haven't done it, then please do so, but we will start with the hands-on session. Yes, so in the first cell, you can actually read the instructions of how to run this notebook. So first of all, this notebook will not generate any files for in your Google Drive. It will all go into the temporary directory. So afterwards, there's not that much to clean up. So you don't really need anything. To run it, you need to have a Google account. But since you copied the drive, the folder to your own drive, your own Google Drive, that should be taken care of. So we're going to run the cells. And for people that are not familiar with IPython notebook, you run a cell by doing Shift-Enter. If you need to completely restart your notebook because you have messed up your global variable, on some questions and problems that I pose. And then you will just be working maybe in small groups with people next to you. Okay, so first of all, to be able to use STScI, you need to install it. So the first cell, if everybody can join me in running it, just Shift-Enter the first cell, and it will take about a minute or two for all the code to install. You can see it's installing everything. Okay, that's done. So I cheated a little bit because I already installed it just before you all entered the room. So this one is going much quicker than yours. Yeah. So now I don't know how long I need to wait. So I'm just going to wing it a little bit. Okay, so while we're waiting for this to install, you can already go to the next cell, Shift-Enter, and then it will import all the correct code. And then we go to the third cell where we have a helper function that will help us throughout the code. And this is a function that generates videos for parameter studies. So that's really useful. Okay, so now we have run these three cells, and then I will explain a little bit about STScI. One of the reasons why we developed STScI is because STScI runs or optical propagation modeling is like the fundamental thing for coronagraph studies and other optical propagation things is the Fourier transform. Numerical implementations of Fourier transform can wildly vary from person to person, from code base to code base. And 10 years ago, when we were working on chronograph designs at Leiden Observatory, we were working on that with like 5 or 6 different people, and everybody had their own Fourier transform code, which made it very complicated for us to share chronograph designs between us, which is why we started to develop this common package so that everybody had access to the exact same implementation of the Fourier transform. So we could do exactly the same numerical propagation that allows us to actually share chronograph designs. So in principle, doing a Fourier transform, implementing it is not super complicated, but everybody makes certain assumptions, and that makes it difficult to share code. So having a common code that works is great. Okay, so I guess everything should now be roughly installed and everybody should have run the first couple codes. So this first block is, we don't need to understand it right now, but this first block generates a PSF from a certain aperture. And at the end of the first block, we should understand everything that's in this cell. Yeah, so I'm just running the code now, so we will go back to it again later on. Just run the function and then run this one, this cell. So now it's making an animation of this code and what we're going to vary. So we're making an animation, so that's making this video. And we're calling this function pupil focal planes that we just generated. And what we are varying is the wavelength. So we're varying the wavelength from 0.5 to 2.0. And this is effectively in normalized units. So you can also think about this, we're scanning from half your reference wavelength to double your reference wavelength. That's how you can think about it. And then we can look at the PSF. So here's the animation. You should be able to run it. And now we see then when we step through wavelength, that the wavelength causes the PSF to grow. And that's due to diffraction. So this morning when we were talking about diffraction, you have lambda over d, which is the fundamental resolution limit. And it grows with lambda. And that's what we're showing here, is that when you scan through wavelength, you can actually create bigger PSFs. So everybody should be able to get this video by now. So congratulations, you have simulated your first PSF. Okay, so that's the goal, to understand how all that code works. So first, I'm going to give a bit of an introduction to how HCI works, what we do in the background. So HCI works on the basis of what we call physical fields. A field is a mathematical object, and it originates from physics. So it's a mathematical physics thing. And a field is any quantity that varies with space. It's very abstract, but you can make it much more concrete by thinking, for example, about temperature. If you think about temperature inside this room, we can actually measure the temperature at all different points in this room. And then if you have an object that tells you, or a function that tells you what the temperature is everywhere in the room, then we have the temperature field. So a field is just something that returns a value for a position. And temperature is an example of a scalar field because it's one number for one position. But we can make it bigger. We can, for example, go to vector fields. The electric field is an example of a vector field because of polarization. Electric fields have an X component, a Y component, and a Z component. And you should not confuse them with the X, Y, Z position, but it's the electric field component in the X, in the Y, and in the Z direction. So that's the electric field vectors. But those can also vary over space, which means it's a vector, it's a field, but because it has vector components, it's a vector field. Then you can go one step further and you can do tensor fields. And tensor fields are when you have a varying tensor as function of position. An example is, for example, the stress energy tensor of the electromagnetic field. But we don't use that. So that's fine. Okay, so if you have a field, that means you have a value somewhere and a position. What HCI needs is knowing what positions the values are corresponding to. So we need to have a grid. So the grid tells you the positions where everything is. And that's why a grid object is the fundamental unit of HCI. So here we are creating a uniform grid that has 11 pixels in one direction, 11 pixels in the other direction, has a horizontal size of 1 and a vertical size of 2. So here you can already see one thing that's different in HCIPy from other libraries is that we define everything in X, Y, Z, and we don't do YX, which is the normal indexing for NumPy arrays or other arrays. So just try to remember in HCIPy, we are doing X, Y, and not YX. Oh, yeah, I can also show the pointer. Whoa, there it is. So X, Y, and not YX. And if we plot all the points, so here we have our grid, and we can get the X coordinate, and we can also get the Y coordinate of the grid. So here I'm plotting the X and Y coordinates of every pixel. And we can see we have a nice 11 by 11 pixel grid with two different axes. One is 1 meter broad, is 1 meter wide, and the other is 2 meters tall. So this is the fundamental thing, a grid. So a grid just defines where the values are, or defines the positions of the values. So this make uniform grids is very helpful because it makes uniform step-sized grids in arbitrary number of dimensions. But usually we only have 2 dimensions, which are X and Y. It's a 2D plane in optics because we go from one plane to the next plane, to the next plane, to the next plane. So that means it's usually 2-dimensional. That's why we also have a helper function, which we call make pupil grid. And this helps us to do it much quicker. So instead of giving the dimensions for every, giving the size for every dimension, we just give it a single size, and then it automatically makes a 2D grid. So this is just to help you and to reduce the amount of time that you need to spend typing. So that's for the pupil plane. For the focal plane, it's a little bit more complicated. So here, one of the nice things about Google Colab is if you put a question mark behind a function or a member method, it gives you the documentation. So we can actually run this cell and get the documentation on the side, and it actually tells you what's in our documentation. So we try to document all the functionality of HCIPy. It's not completely documented, but I think most of the important parts are documented. So one of the things you see in the signature of make focal grid is that it's actually very complicated. We have like many parameters. And that's because originally we made it with a different set of parameters on how to make a focal plane grid. And then after about 2 or 3 years of using this, we figured out that it was actually not helpful, and we switched to a different interface. But to make sure that all people's code does not break, we kept the old interface, so that's backwards compatible. And that's also what we explain in documentation. So the things that should matter for you if you make a grid for a focal plane is Q, or also wait, this is maybe better. Q, which is here, there, is the number of pixels per resolution element. For example, if you take lambda over d as your resolution element, Q tells you how many pixels you have per resolution element. So if you want to have 15 pixels per lambda over d, you use Q as 15. And then the second part, how does this work? Do I need to stand here? Yeah. Okay, so the second part is the number of array rings. So that's just how many lambda over d do I want the field of view to be. And then one of the important thing here to remember is that that's radius. If you choose 10 array rings, that means you have rings to the right and rings to the left. So that means you get twice the field of view. And then finally, spatial resolution, which is just how big is lambda over d in radians. So that's what you add. Okay, so that's all about grids. So with this, you should now be able to make grids. You can always read up the documentation and or the text that I have around these blocks to go back to. So now let's make a grid for a pupil. We make it 128 pixels. I make it 1.1 meters because I usually like to oversize my grids a little bit compared to the actual physical size of my aperture. That helps to reduce edge effects, numerical artifacts from the edges. So we run it. Great. We have made a grid for a pupil. Then now it's time to write a circle function. So here I'm showing how you make a circle. with this grid. So first, in this function, we put the circle diameter. So how big do we want to have the circle? We put the grid on which that we want to evaluate the circle on. And then we take access to the x coordinate and the y coordinate. And then with x and y, it's very easy to calculate the radius. It's just x squared plus y squared, Pythagoras. This is not super complicated. And then we make the actual circle, and it means that we make a binary mask. So all the pixels are valid that are smaller than the diameter divided by 2. So we just select all the pixels that fit within the radius of the telescope. Well, we have done that. Then we need to convert them to floats because that's a thingy from Python. And then we make a field. And as I said before, a field has values, which in this case is the circular mask, and it has an associated grid, which is here. So values and grids, those are the two things together that make a field. And when we evaluate this on our grid that we made, oh wait, I need to, of course, run this one first. Oh. And then we can run it. And now we have made our telescope aperture. Well, it's not visible because we have not plot, because we did not plot it. So let's do that. HCIPy has a convenience function, which is imshow field, which actually is very similar to the normal imshow from matplotlib, but then works with the field objects from HCIPy. So if we run that, we can actually see our circle function that we just made. So I hope that everybody now has a circular aperture, that we all can run it. So that's great. This is not a very efficient function, and we have actually better internal functions for circular apertures. So it's much better to actually use the internal function for HCIPy, which is make circular aperture. It's very logical name. One of the complicated things here that I want to mention is that we made this using something called a function generator. So this is a function that returns another function. That's not a very, it's not something that astronomers use a lot in their normal software life. So that's why I want to explicitly explain it, what it is. So it returns a function that is evaluated where you can pass a grid to. So the reason why we did this is that this is a sort of an abstract function now that always makes an aperture of size 1. And if we generate a grid, for example, this low resolution grid that has 32 pixels, we can actually evaluate the aperture on this low resolution. Oh, wait. I need, of course, to run the cell. I'm not listening to my own advice. I'm just reading the text. We run this, then we run this. Okay, so now we have a low resolution pupil. But because of this function generator, we can also create a high resolution grid that has 512 pixels instead of only 132. So if we can, and then we can actually evaluate the same function on this pupil with this grid. And then we can actually generate the two different pupils. So we have a low resolution pupil and a high resolution pupil. And this is the thing that is why we implemented the function generators, because this sort of decouples the creation of the aperture from the sampling. And you can do arbitrary sampling with your aperture. And you can change the sampling on the fly. Okay. Almost done with the basics of HCIPy. Almost. The last thing are wavefronts and optical elements. And as Eva explained this morning, wavefronts are electric fields. Those are the things that actually do something in the code. And the wavefronts, they interact with optical elements. And an optical element here is meant as something very abstract. So usually when we think about an optical element, it's like a lens or a transmission filter or a color filter or a deformable mirror. But in our case, an optical element is more abstract. It's something that accepts a wavefront or an electric field as input and spits out another electric field. So it's anything that changes the electric field. And in this case, the Fraunhofer propagator that we have, which was explained this morning as the Fraunhofer diffraction integral for the far field transform, is also an optical element because it takes a pupil electric field as input and it outputs a focal plane electric field. So not only optical elements are like actual physical optical elements are optical elements, anything that interacts with the electric field is an optical element. Okay, and then here we have the wavefront and we can see and look at the documentation of the wavefront, what you need for it. And let's see, how we initialize it is with an electric field. That's what's said in documentation. You can give it a wavelength. You can even give it an input Stokes factor. So what I was saying during the morning session, that HIPA was made with polarization included in its design. And that's here because you can change the Stokes factor of your wavefront. Well, for us, we are just going to ignore polarization, so you can ignore it for today. But later in the future, if you want to do polarization modeling, it's relatively easy to do with HIPI. You only need to change the Stokes factor. And that's about it. So here we are showing how you, for example, generate a propagator. So if you have made a pupil grid and you've made a focal grid, then you can just pass that on to the Fraunhofer propagator, and then it figures out by itself how to do the Fourier transform correctly for the pupil sampling and the focal plane sampling that you chose. Because it's not easy. You cannot always arbitrarily do an FFT. You need to do a lot of numerical stuff to make sure that the samplings are correct and that it's energy conserving. So there's a lot of things in the back that are happening here. Okay. So in summary, HIPI uses fields, and for fields you need to have the values and the grids, and then you can pass a field to a wavefront, and then the wavefront goes through optical elements. Okay, so now we are reaching the part about apertures and PSFs, and there are some questions for you. So please go through this part by yourself or with people around you and discuss the questions that you see here. And we will take about, I would guess, about 15 minutes for this part. I will put a timer on, and we will know very well if it ends or when it ends. So please go ahead and try it out and try to figure out the questions. So what should the helpers go around now, or? Yeah. So if okay. So if you have a question about anything that you're running now, please raise your hand. Then either me or one of the helpers will go to you and help you. Okay. So we have done the first part. So I hope everybody had fun discussing this with your neighbors or with other people, or just thinking about it. There will be a solution manual with the answers, but I'm not going through them now. You can look them up afterwards. Or you can continue thinking about it. Okay, next step. After making simple apertures, we can actually, with HIPI, we can go through almost all the telescopes that we have made or are interesting. There are a couple ones that are still missing. So if you ever are in a position where you're like, oh, I really made an aperture that's not on the list of HIPI, please make a pull request on the GitHub page, and then we can add your favorite aperture. For example, an obvious one that is missing is the Large Binocular Telescope, which is not on here. So we're still missing the LBT. But we have many other telescopes, such as ELT, GMT, TMT, the Magellan, LUVOIR A and B, the Hill Telescope, VLT, HABEX, HST, James Webb, Keck. So we can actually make all the apertures from this list. So now we need to wait a little bit. And there it is. So now we can actually look at the PSFs of all the apertures that we made. And you can see they're all pretty different. But one important thing that you see that stays roughly constant is that regardless of the aperture, it's the central part of the area pattern is always roughly the same size. It varies maybe with about 10 or 20%, but it's always on the order of lambda over d, regardless of the shape of your aperture. And you can also see when you run through this is that the PSF, the symmetries in the PSF are reflected in the symmetries of the entrance pupil. So if your entrance pupil has 6-fold symmetry, then your PSF usually also has 6-fold symmetry. And yeah. Okay. So now we know how to make apertures. And if we know how to make apertures, we can actually start making coronagraphs. So we're going to the second block. And we're going to work on coronagraphs. Okay. So the first thing to do for the vortex coronagraph is to make the focal plane mask, which is that phase-wrapped focal plane. So that's what the first code block does. Here we're also showing the focal plane mask. So it wraps around twice because we chose a charge of 2. Later you can change the charge if you want to. The reason why we're choosing the vortex is because it's an ideal coronagraph, as David explained this morning for clear apertures. So for the rest of this block, we're just going to work with a clear aperture. So that's a normal circular aperture. That makes it easy to understand everything. Okay. So the first thing we're going to do is we make our pupil aperture. We choose a diameter of 1 because we work with normalized units. You can also choose 10 or 20, but then everything scales. So we keep it simple to 1. Our LEO stop needs to be a slightly undersized compared to the entrance aperture. And that's because we want to make sure that no light enters to our LEO stop. And then again, we need to go from a pupil grid to a focal plane grid. So we need to create a pupil grid. So here you can see that we're using 1024 pixels in the pupil. So that's quite a lot of pixels. But if you want to accurately simulate a vortex coronagraph down to the 10 to the minus 11 level or 10 to the minus 10 level, you need to use many pixels in the pupil because you need to accurately represent a circle. And you think that's weird, but with 1000 pixels, that's just about enough pixels to actually simulate a circle well enough to reach 10 to the minus 10 contrast numerically with a vortex coronagraph. Okay, so then we also have a propagator because we want to go from a pupil plane to a focal plane at the end to look at our science images. And then here we generate our pupil. So here you can see another convenience thing that STScI has. And because the make circular aperture function is a function generator, we can actually pass it to evaluate supersampled. What evaluate supersampled does is it supersamples this circle by a factor 4. So that means it actually calculates the circle function on a 4 times higher resolution, and then it bins it down to do anti-aliasing to remove high spatial frequency artifacts. And that's also actually another thing that's necessary for the 10 to the minus 10 contrast. So for 10 to the minus 10, I actually need to have a native resolution of 4000 by 4000 pixels. But doing it at 4K by 4K makes your simulations really slow. And that's why we apply anti-aliasing filters at lower resolutions to make sure that we can actually speed up the propagations a little bit. So there's a lot of thinking that you sometimes need to do to make sure that your results are correct numerically. And that's because 10 to the minus 10 is really small. It's really challenging. So also numerically, it's challenging. Okay, then we make a vortex coronagraph, which is just a vortex coronagraph. It's not a lot of surprise there. Then we give it a pupil grid because we want to know at what entrance plane the coronagraph works. And then we need to pass it the grid, the charge. So, and the reason why it works in the pupil grid is because all the coronagraphs that are implemented in HCI go from the entrance pupil to the Leo stop plane. And it does the calculations for the focal plane mask internally. And this is because of, like I said, doing 10 to the minus 10 numerically is challenging, especially for the vortex coronagraph. So the vortex coronagraph wraps around like a vortex, and in the center, you have a singularity. And to sample that singularity well enough, you need to use 64 pixels per lambda over d. And 64 pixels per lambda over d for the full grid that's already 1,000 by 1,000 means you need to simulate 64,000 by 64,000 pixels in your focal plane. And that's computationally very, very expensive. So HCI does a very complicated multi-scale Fourier transform where it actually does multiple scales. And then it does an accurate propagation of the vortex. So that's why this is another reason why using HCI is really useful instead of implementing it yourself, is we use advanced numerical algorithms to do accurate treatment of certain coronagraphs to make sure that you don't run into numerical issues. And then at the end, we make our Leo stop mask. So first we make the field, which is the Leo mask. And then we give it to an apodizer to make it an optical element. Because just having a field doesn't mean that the wavefront or the electric field knows how to interact with it. So we need to make sure that we tell the code how to interact with electric fields. So that's here, it just becomes a normal apodizer. So an apodizer is anything that just transmits and modifies the electric field. So we run it. It takes a little bit of time because of the 1024 pixels in the pupil. So now we need to wait. It's done. And we can actually make a figure. And then we see what the vortex coronagraph does. We have an entrance pupil, we have a focal plane mask, and we have a Leo stop. And this Leo stop is a little bit undersized compared to the normal pupil. Okay, and then we actually generate a wavefront at the beginning. And the only thing we pass it is the electric field that we want the wavefront to have at the beginning. And in this case, we assume a diffraction limited wavefront. So that means its amplitude is just the pupil and its phase is 0. And that's why we only pass it the pupil. Then we propagate the wavefront through the Leo stop. So we remove the focal plane mask and we propagate it through without a focal plane mask and look at the image that's created. And that's this PSF on the bottom. And the reason why we do that is because we want to know the peak of the PSF so that we can actually normalize it to get the raw contrast or the normalized intensity so that we can make pictures of the normalized intensity. Yeah, so this is what I explained, is that it's non-trivial to do actually accurate 10 to the minus 10 coronagraph things. Okay, so the actual implementation of a vortex coronagraph is we create a wavefront with the pupil. Then we can propagate it to the focal plane to make a reference image. And that's separate, so this is separate from the rest. Then we propagate the wavefront through the vortex coronagraph, and then we get the electric field just before the Leo stop. Let's also run this. Then we apply the Leo stop. So now we get the electric field after the Leo stop, so where all the light outside of the geometric pupil is blocked. And finally, we propagate that to our science image plane to get the image out. Well, so it's a lot of work to constantly rewrite this and do everything with it. So we make an additional function that does this for us and at the same time also plots the wavefront at all the planes. So this is again a convenience function to quickly change the incoming wavefront, and we can look at everything. So we run it again. Okay, I'm going through it. So now we create a diffraction limited wavefront and we call this function. And what happens should not be a surprise, but if you have a diffraction limited wavefront going through a vortex coronagraph, there should not be any light left at the end of your science camera. So here you can see we have the light at the entrance pupil. This is the PSF that hits the focal plane mask. This is the light at the Leo stop. You see that the vortex has scattered all the or diffracted all the light outside the geometric pupil. Here is the Leo stop or the area that we pass through. And if we apply this Leo stop, nothing is left of the starlight. And that means that in the focal plane, there's also nothing left. So again, congratulations for everyone. You have now simulated the chronograph. But what happens when we have an off-axis source? Because that's an important thing for the chronograph. It suppresses on-axis light, but passes through off-axis light. Because otherwise the chronograph is not convenient. We want to propagate a PSF at 1.5 lambda over d. And you can do that by just modifying the entrance wavefront here. Let's see if this works again. So we have the entrance wavefront and the amplitude is still the pupil, but then now we actually have phase, which is the tilt. And that phase is 2 pi times the pupil grid in x times 1.5. And if we do this, then we can actually simulate a planet or an off-axis planet. So again, we have the light at the pupil plane, the PSF at the focal plane mask, the light at the Leo stop. The Leo stop blocks light that's outside of it, so pass through only the center. And then we have the final science camera image. Okay, so now we know how to simulate light through a vortex chronograph. Now there's a couple questions again for everyone that we can work on. So in this case, let's see how much time. I will give you about 20 minutes for this. So there are 3 main questions that you should try to answer. And then there are 2 bonus questions if you have time left over, or if you're quick with the other questions. Okay. So 20 minutes and go. The timer didn't go off this time because I was just in time to stop it. Let's continue with the next section. It's okay if you haven't finished all the questions. You probably have the rest of the week to think about it. And if you actually do something with direct imaging, you can actually think about it for the rest of your undergraduate degree or your master's or your PhD. If you have nothing to do, you can always go back to the notebook and think about things. Okay. So now that we know how to simulate a vortex coronagraph, we need to analyze it. We need to figure out, like, what are the metrics? Like David showed this morning, if we want to know how a coronagraph performs, we need to know how to analyze it to get throughput, get inner working angle, get all the quantities that we need to know. So the next part of the notebook will be focused on, like, how do we derive all those numbers? Okay, so the first thing is, how do we measure throughput? It's a very interesting question because there's a lot of discussion about how you measure throughput. It's actually not as trivial as you might think. So do you measure throughput as the light that passes through the Leo stop? So if we look at our planet PSF, and if we look at an off-axis angle, for example here, which parts of the PSF do we include in our throughput measurement? Is it useful to add all the light that we see here that's far away from the planet? Probably not, because at those points, the noise from the star dominates. So there's photon noise, read noise, all kinds of noise sources at those pixels. So if you add those pixels into your measurements, then you're actually adding more noise than you're adding signal. So if you want to do signal to noise optimal measurements of your planet, you need to think about which pixels actually give me the most benefit in terms of signal to noise gain. And then if you start to think about that, then the pixels that actually give you the most gain are only the pixels here in the center and the core. So only the core pixels for planet light matter, because all the other light will just add noise from the star. So that's one way to measure throughput, is we only measure the core throughput and not the throughput in all the rest of the diffraction rings. So as you can see, it's not a simple question, what's the throughput of your chronograph? Because you need to think about the signal to noise of your measurement to actually come up with an optimal aperture. Okay, so for the purpose of this hands-on session, we define the throughput as the light that passes through a 2 lambda over d circular aperture. So, and the 2 lambda over d is the diameter. So, and to highlight that, here is our PSF, and you can see the circle within we measure the throughput. And that's the only light that we consider for throughput. The rest outside of it, we throw it away because that's just noise. So now we can simulate throughput again by going through different angular separations. We go through our vortex, we go through our Leo stop, we go to our image science plane, and then we make a photometric aperture. So we make the circles where we sum up the pixels, and those circles move together with the position of the planet. So here you can see that we move the planet, or move the circular aperture. And here you can see we use the make circular aperture function, which we also use to make the pupil. But in this case, we make it to do a circular aperture in the focal plane. And to do that in the focal plane, we just pass the focal plane grid instead of the pupil grid. And that's another way to show how easy it is to use these pupil function generators. You can use them in a lot of different contexts. Okay, so we're waiting because this takes a while because I am simulating 100 off-axis angles to get a smooth curve. Yeah. Oh, we need 1 more minute. Okay, so it's a bit slow. And after this, we have another session with questions and some work that you can do. For that, we will use another 20 minutes. Also, if you need, like during the next session, if you feel you need a break or you need to go to the bathroom, just do that. Because we've been sitting here already for almost 2 hours. We're done with the break in this section and we're going to continue the notebook. Please hang on. It's only another 30 minutes and then you're free. I think. I don't know if there's anything in the agenda in 30 minutes, but. Okay. Some people have dinner tonight. So I probably will have to let you go. Yeah, so the next thing that I wanted to show is what happens if you have a central obscuration. So if you change your pupil aperture, so instead of having clear aperture, that's theoretically perfect for a vortex coronagraph. What happens if you actually change the central obscuration? So here we have the same type of function as we did before, where we just change the central obscuration and we make a video of it, but now with the vortex code. And here we see perfect clear aperture, perfect nulling, but if we increase the central obscuration, we can actually get more leakage. Oh, and this is maybe an old version. And you can also see I messed up the Leo stop because the Leo stop now is made for a clear aperture and it's not made for a central obscuration. And you can see here that the reason why we have leakage is because the vortex creates another ring of light around the central obscuration. So just how it pushes out the light to the edge of the normal pupil, it also pushes out light to the edge of the central obscuration. And that's very difficult to block. And that's the reason why for telescopes with central obscuration, the vortex leaks light like that. Yeah, so we can also simulate non-perfect pupils. So, and this also means that actually the coronagraph should be matched to your pupil geometry, which was also explained this morning by David. So it's always important, like the coronagraph matches the telescope aperture. Or it should match, otherwise you get leakage. What did I do here? Let's run it. Oh yeah, aberrations. We're now going to the third block, which is aberrations. It's not super long, so don't worry. Like Eva told you this morning, we can make sinusoidal aberrations. Here's a sinusoid with a frequency of 10 cycles per pupil, an amplitude of 0.1. And that looks like this in the pupil. So now we're making a telescope with a central obscuration and 6 spiders. That's roughly similar to TMT or ELT or, well, not James Webb, because James Webb is segmented, but 6-fold symmetry. There's a bonus question for people. that want to look at it, but that's not for now. So now we make another speckle function, and we have a couple animations that run. And where we can see what the effect is of different amplitudes, and what happens if you change the spatial frequency of the speckle. And here we're doing just aberrations and normal PSFs. And the last one is if we change the phase of this sinusoid. So with phase, I don't need the phase of the amplitude, but I mean the shifting the phase of a sinusoid. So instead of having it start at 0, it starts at a shifted phase. So in this case, we have a shifted pattern. Okay, so those are 3 movies. Please run them. And then we have a couple questions for that. So for that, we take about 5 minutes, because actually Eva told you the answers already. So if you have looked at the lecture this morning and listened, then you should be able to answer the questions. Going to the next section. So instead of sinusoidal aberrations, we can also use Zernike modes. So this morning, Eva sort of explained what Zernike modes were. They are an orthogonal basis of functions on the unit circle. And we will show a couple of them. So this is an animation that will show the first 21 or 22 or so. So these are the aberrations, the first low order aberrations. And these are the Zernike modes. So those are the modes that we are going to analyze in this section, because these are low order aberrations that are created by optics that are shifted, tilted, slightly misaligned. Then you typically get these type of wavefront errors. So that's why we analyze them, because those are the ones that have the most power, because they happen the most. So now we need to make a figure, and David already showed that figure this morning, which shows the contrast leakage as function of aberration strength, and this cell simulates all of them. And please follow along. This takes a little bit of time, because you need to propagate quite a lot of wavefronts. Oh no, wait, this is the other one. This shows how well each of those Zernike modes that I just showed are filtered out by the vortex coronagraph as function of charge. So here you can see that the charge 2 vortex, which has the smallest inner working angle, only filters out piston. But then the other modes, they leak through the coronagraph. But if we go to a charge 4, we can see that it removes piston, but it also removes defocus. So this shows that the charge 4 actually is robust against low order aberrations. But because it removes more modes and more light, you actually lose inner working angle. So this is again that tolerancing of that you have between inner working angle and robustness. And you can see that if we go to higher order charges, more modes get filtered out. So, and if we use this, now we're running the slower cell, where we actually reproduce the figure. So please run it on your laptop and then try to answer these 2 questions. And if we have answered those 2 questions, we're actually at the end of the hands-on session. So I will give you 15 minutes, or let's make it, let's make it 15, or let's make it 10. Let's do 10. And then after those 10 minutes, I will use the last 10 minutes of the session to explain the group projects that you can do. Done. Okay, so is it on Thursday, the group projects, or when do people do the group? Yeah, so on Thursday you will do a group project. If you go to the Slack channel for the group projects, there's a link where you can sign up for one of the group projects. So please do that when you have decided which group project you want to do. So tomorrow and the day after, there will be other hands-on sessions where you can sign up for other group projects. So you have some time to think about it. But please sign up so that everybody knows in which group you are. So what we are going to do for optical modeling is that you have 2 choices. The first one is about fast aberrations and adaptive optics, because up to now we've only discussed sort of space-like conditions where the aberrations are slow, we can remove them, we can analyze them. But when we do ground-based adaptive optics, we actually need to simulate atmospheres and we need to simulate PSS through atmosphere. So I'm not going to run this because it takes a little bit of time. So we don't have time anymore to show that, but here is code to actually work through how adaptive optics works and the PSFs it creates. And then for the group projects, we have some questions about how AO performs with different parameters and if you can generate a realistic coronagraph for the ELT. So that's a different type of aperture. Yeah, so I think this is an interesting group project. The other one, which is a little bit shorter, is to work on active wavefront control for EFC. So we have now seen that there are aberrations that leak through your coronagraph, and we actually want to control them and remove them. And that's what we want to do in this project. So part of this project is actually to go to this tutorial from the HCIPy website about electric field conjugation, so the focal plane wavefront control. It will explain you how it works, how you implement it. And then the goal is to implement this in your Google Colab notebook. So a lot of this is just copy pasting the blocks and see how they behave. And then the goal is in the end is to make this video, or in the end, it's actually this video that we want to make, where we can show that we can create a dark hole on one side where we search for planets. And that's the goal of the group project, to be able to do this. And then there are a couple questions that you can work on, which I think are also interesting from the perspective of focal plane wavefront control. So we have made it to the end of the session, and I don't have a lot of more to say, so you can take it over.